Hello, have we got a treat for you today? We're going to be covering atomic structure, which occurs in both your physics and your chemistry, your C1 and your P1. So that's twice the work in half the time. How cool is that? So, without further ado, let's shoot back in time to where it all began, back in ancient Greece. In the barbaric times of ancient Greece, you had to have a sense of humour to survive. And our friend Democritus was no exception. He's affectionately known as the Laughing Philosopher. He suggested that everything was made of tiny, indestructible particles called atoms. However, he was largely ignored for over 2,000 years. He has the last laugh now, because in the early 19th century, John Dalton developed his ideas to suggest that atoms did exist in an element, and they're identical, and the atoms of different elements have different sizes and masses. For example, all atoms of helium are exactly the same. All atoms of sodium are exactly the same as well. But the atoms of sodium are much bigger and heavier than the atoms of helium. But it wasn't until nearly 100 years later that advances in precision engineering created the equipment to allow further discoveries at atomic levels. At the end of the 19th century, Thompson discovered tiny negatively charged particles called electrons, which could actually leave the atoms. Since the atoms have no charge overall, the rest of the atom must be a mass of positive charge to balance out the negative charges on the electrons. And these electrons were discrete particles within this positive mass. He called this the plum pudding model. It's a bit of an old-fashioned concept, but since this was the early 1900s, we'll let this one go. I like to think of it more as a chocolate chip cookie model, the chocolate chip electrons in a positively charged cookie dough. One of Thompson's students, Ernest Rutherford, devised a scattering experiment to find out more about this cookie dough mass of an atom. This consisted of a black box on the left, firing radiation of alpha particles at a thin gold leaf in the centre, and observing how these particles scattered over a curved fluorescent screen. Alpha particles are positively charged helium atoms, and he found that most of them went through the gold leaf to suggest there was a lot of empty space in there. However, some of them were deflected on the way through, suggesting that they were knocked off course by a dense, heavy, positively charged nucleus, while some simply bounced back off this nucleus. And this led to the atom idea that we know and understand below. Only a couple of years later, Niels Bohr proposed that electrons orbited the atom in organized shells. 20 years later, Chadwick came along to discover the presence of uncharged particles in the nucleus, called the neutron. So here we now have our current understanding of an atom, consisting of a dense nucleus of protons and neutrons, with electrons orbiting in organized shells. What Rutherford found when he fired these alpha particles, or helium nuclei, positively charged helium nuclei, at the gold leaf, he found that most of these alpha particles went straight through. Occasionally they go through but deflected at the other side, and sometimes they bounce straight back. The ones that bounce straight back must have hit a big heavy nucleus of the gold leaf. If they went through but were deflected, then there must have been a positively charged nucleus for them to be repelled through. Now, for every one that's repelled through, deflected, or bounced back, 8,000 of them went straight through. That seems to suggest there's an enormous amount of space inside an atom. In fact, if this was the size of the gold leaf nucleus, the orbiting electrons would be a kilometre away. So, to summarise then, the charge on a proton, P for positive, P for proton. The charge on an electron being negative, but the charge on each are equal and opposite. So if you've got a charge of one proton, you're going to have one positive, you're going to have one electron, one negative. The masses are similar to that of the neutron and the proton. In other words, they're around about one, but the electron is just so small compared to the others, we say it's negligible. In the periodic table, the elements are always listed with two numbers. First of all, you've got the symbol Na, for example, which is sodium, and two numbers. One is the mass number, and one is the atomic number. Now, when we think about mass, we generally think about big. Large mass is going to be big. So the larger of the two numbers is the mass number. And as you've seen before, the mass of an atom is its nucleus. So the mass number tells you what's inside the nucleus. In other words, the number of protons and the number of neutrons. The atomic number, the smaller of the two numbers, is the number of protons. It's the number of positive charges. Now remember, an atom is electrically neutral. So if you've got 11 protons, 11 positive, you're also going to have 11 electrons. So the atomic number then is the number of protons and the number of electrons. How do you work out the number of neutrons inside the nucleus? Of those 23, 11 of them are protons and the rest are neutrons. So take away the number of protons, you're left with a number of neutrons. Number of neutrons, subtract the two numbers, that's 12. It's important to note that the number of protons in an atom of an element is always the same. That's exactly what John Dalton was saying back in that history presentation earlier. If it had 11 protons, it's going to be sodium. If it has 12, it's not sodium anymore, it's actually magnesium. However, you could get different numbers of neutrons in an atom. And if you have different number of neutrons, it's going to be an isotope of that element. For example, hydrogen is the simplest element. All it is one proton. But occasionally you might get a hydrogen atom with a neutron in it as well, such as the 2,1 hydrogen. Or even 2 neutrons, such as the 3,1. These different isotopes with the extra neutrons are heavier, and you can use these heavier types of atoms of particular elements in scientific studies. Now if you get the number of electrons, these electrons can come and go on and off an atom, and if an atom loses electrons, we call it an ion. The understanding of the ions is essential for when you come on to things like ionic bonding and electrolysis later on in your course. So, looking again at the mass of the electron, it's kind of difficult to get bogged down with all these noughts, so there must be a way of grouping all the noughts together. If you move that decimal point 4 places to the right, you're left with a whole number 5. So you can change that to standard form. In other words, the mass of electron is actually 5 times 10 to the negative 4. Negative meaning you're moving it to the right 4 times. Now, the size of an atom, or the radius of an atom, is round about the sort of 10 to the minus 10. It's often referred to as 1 angstrom. And if you take, for example, the radius of an oxygen atom, well, that number of noughts is 7.3. But if you move the decimal place 10 times to the right, you're left with 0.73 times 10 to the minus 10. So that's a kind of standard form for presenting the radius of atoms. Names of the sizes generally increase or decrease by powers of 3. The oxygen atom, 0.73 angstroms. You could say that's 0.073 nanometers or 73 picometers, whatever. To get a better understanding of size, let the deep, soothing, godlike voice of Morgan Freeman take you on a journey into the inner world. But before we do, if you'd like to take a screenshot of this presentation, I'm just going to shrink myself down to the size of an atom.
microscope allows us to continue our journey into the realm of the very small. As we move into the cell nucleus, each new ring now reveals a world 10 times smaller in diameter than the last. Deep within the nucleus, we come upon truly remarkable constructions, long spiraling molecules of DNA. DNA holds the chemical codes for the reproduction of most organisms on the planet, whether they're paramecia, people, or petunias. Voyaging on, we see that molecules are made of even smaller parts called atoms. The tiny world of the carbon atom is very strange indeed. Its 6 electrons seem to swarm everywhere at once. Now our voyage takes us through a void that appears as vast as the space between the stars. Ahead lies the atomic nucleus, so fantastically small that if the whole atom were the size of this theater, its nucleus would be like a speck of dust. Yet the nucleus contains almost all of the atom's mass, packed into particles called protons and neutrons. And these, in turn, are made of still smaller, mysterious things called quarks. Exploring this, the inner frontier of the universe, physicists wonder if quarks might contain even tinier building blocks of matter.
Did you know that Morgan Freeman's voice has been insured for $250 million? Anyway, if you've got any questions about anything we've covered today, put them in the comments section below. You've heard the distinct and godlike voice of a famous actor and narrator. And we've covered the use of helium in scientific research. So I know what you really want to ask. So here's your answer. It's Morgan Freeman on helium.
In unusual situations,
you don't always get what you expect.
But sometimes, unusual situations lead to new insights. To find the truth about gravity, physicists are studying it in a place where they expect it to
act very strangely.